Okay, good morning, everybody. So today is going to be a lab session, and we're going to implement Monte Carlo and temporal difference learning for estimating the value function of a fixed policy. So you can open the usual folder, arc/rl, and inside that folder, today we're going to work on exercise number 3. So that's the main script, and as usual, the solution is going to be implemented in a different file, which is inside the sol folder. And you have the two versions, the one empty, which you should fill in, and the solution already implemented by me, which is the one with finishing with _prof. The idea for today is that we are going to start by implementing Monte Carlo, and I'm going to do the implementation here live. And then I'm going to give you some time to do the implementation of temporal difference, which starting from Monte Carlo shouldn't take you too much time because it's quite similar once you have the code for it. We're going to work as usual with a pendulum, 1 degree of freedom, extremely simple because it's a low dimensional state space, so it completes fast. And the policy that you're going to find in the script is the same one that we have been seeing before. So it's the one that I designed by hand, which is trying to stabilize the pendulum in the top configuration, but not doing a very good job at it, if you remember. Of course, you're free to change it with a different policy or to try to tune this to work a bit better. Then here we have the main script. We generate a random seed because, well, now we have a stochastic algorithm. And so the result is going to depend on the random seeds that we use for the random number generators. So what I do is that I take a random seed at the beginning and I print it. So in case you want to repeat exactly the same execution, you can just fix the random seed and rerun it. Then you can decide, well, the environment, you have these two environments, pendulum and ABC. ABC is the one we have been seeing in the example in class, but it's not very interesting. It's just a three-dimensional state space. We're going to work with the pendulum period. Then here you have all the hyperparameters. So discount factor, which is pretty small, 0.9. Number of episodes that we have to run the algorithms for, the length of each episode, the learning rate, in case you're doing TD learning, you have to decide the learning rate alpha. Here we are using very large values, then we're going to discuss why, so 0.5 and 1. Remember, the learning rate is typically between 0 and 1, and in practice, people tend to use values that are closer to 0 than to 1, but in this case, it makes sense to use large values. Convergence thresholds, this is not for Monte Carlo and temporal difference because they don't have a convergence threshold typically. You just decide how many episodes you run and that's it. This is for running policy evaluation at the beginning so that we have the ground truth value function that we can compare against. Noise of the environment, in case you want to add noise on the environment to make it stochastic, you can do it here, but by default it's set to 0. And this is how often it prints stuff. And by default, it should be every 200 iterations. So it's going to print stuff basically 5 times throughout the execution of the algorithm because you're doing 1,000 episodes and you're printing every 200. Here is the creation of the pendulum environment, deciding how much you want to discretize the state space. The feedback gains for the policy. And then as a first step, we just compute the value function using policy evaluation. And this is going to give us a ground truth. And after you have the real value function, well, you plot it. And then you call Monte Carlo policy evaluation for computing the value with Monte Carlo. And then you do a for loop for every value of the learning rate, which you can try many of them. It's going to call TD0 policy eval, specifying the given learning rate, which is alpha. It's this value here, alpha. And then at the end, it's going to do a plot for each method. So for Monte Carlo and for all the different versions of temporal difference learning, showing you how the estimation error between the estimated value function and the real value function was over the iterations of the algorithm. So we can compare the algorithms to see which one achieves the best estimation error depending on the number of iterations. So they should all go down, but some is going to go down faster than others. So inside this script, you don't have to change anything, at least not in the beginning. Our implementation is going to go inside this second script, where we have two basically empty methods just filled in with comments, one for Monte Carlo and one for temporal difference learning. So before we implement Monte Carlo, we can take a look at the slides. So the idea of Monte Carlo policy evaluation was very simple. You have a Markov decision process of which you don't know the dynamics. You have a fixed policy. So you can just run the Markov decision process using the given policy and collect data. This data is going to come in a flow of state, control, cost, state, control, cost. You're going to have this very long list of state, control, cost as you collect data on the system. Then once you have collected data, what you can do is that for every state that you visit, you compute the total cost to go. It's going to be discounted. So if you visit a state X at time T, then the total cost to go is going to be the summation of the cost you have encountered from time T until the end of the episode, discounting by gamma the future states. So it's going to be this value J over here. This is giving you a sample of what is the value of that state. Of course, if this process is a whole process, so cost, dynamics, and policy is deterministic, then this value is going to be the same every time you pass through that state. And so just one sample is going to be enough to get the correct value for that state. If, however, there is some stochasticity in the environment, then every time you pass through the same state, you're going to see a different total discounted cost. And so you have to collect several samples and make an average, which is what Monte Carlo does. So Monte Carlo, in terms of algorithmic implementation, is going to look very similar to what we see here in this slide. You're going to have a counter n for every state, and we increment this counter every time we visit that state. We're going to have a total cost variable C for every state, which we're going to increment with the cost to go that we have computed starting from that state. And then our estimate for the value is going to be basically the ratio between these two variables we have defined above. So the total cost divided by the number of times we have visited that state. Again, if it's deterministic, actually, we wouldn't really need to keep track of the cost we encountered every time because it's going to be always the same. But we're going to implement this algorithm in its more general form, which accounts for stochasticity. And that's it, basically. This is the algorithm we need to implement. Yeah, this is just another way of writing it, but it doesn't make any change actually to the result. So let's start implementing with Monte Carlo. Let's start taking a look at the inputs we have. We take as input the environment, which is going to be the pendulum, gamma, which is the discount factor, pi is the policy that we want to evaluate, and episodes is the number of episodes that we have to run the algorithm for. Max episode length is how long each episode should be. VReal is the real value function that we have computed with policy evaluation. And that is just needed here for plotting stuff or printing stuff, like what is the current error that we are making. Plot is a flag to decide whether we want to plot stuff or not. And print is how often we should print and plot stuff. And as usual, here you can see we have a very verbose list of comments that is guiding us in the implementation of the algorithm. So let's start following the instructions. We should create a vector n to store the number of times each state has been visited. So that seems easy. We create just an array of nx elements, and we set them all to 0 to start with. We do the same for the cumulative cost, C. And we do the same for the value, which actually was already done here. And then it also suggests create a list vr to store the history of the error between real and estimated value table. Also, this one was already done, so we just move it here. This is not really a part of the algorithm. This is just for doing the plot at the very end to show how the error evolved through the iterations. Then we need to do a for loop for every episode. So for k in range and episodes. And at the beginning of each episode, we need to reset the state of the system to some random state. And we can do that by simply calling emp.reset. And I think this gives us as output the new state. So now it's the comments say keep track of the states visited in this episode and keep track of the cost received at each state in this episode. Simulate the system using the policy pi. Okay. So now we have to run an episode. So it's going to be another for loop for t in range max episode length. And if you remember, well, first of all, we need to compute the control, which is going to be pi of x. And then we have the method step of the environment, which takes as inputs the control, and it gives us the new state and the cost. So this is just for basically running the episodes and collecting data, but we need to store this data somewhere. So I suggest that we create a list of states and a list of cost.
We already have a list for the cost.
So C is the list of cost to goes, not the list of the cost at each step.
Okay.
So it's a list that contains basically the value J. If I use the same notation I was using here, J. Instead, the list I just created is for collecting L, which is the instantaneous cost. Yeah, it's tricky. You should have a clear distinction between these two terms. They're both cost, but one is the instantaneous cost that you get at a given time step. The other one is the cumulative cost from that time until the end of the episode.
D was the cumulative, accumulated cost list.
Actually, so L is instantaneous cost, J is the cost to go, so from a given time until the end of the episode, and C is the summations of the cost to goes at a given state. So there are three different costs, if you want. So actually, the list of states, we can, instead of creating it empty, we can create it with the initial state already inside. And then we can add the state that we just visited and the cost that we just received.
The step function gives us the next step, correct?
The next stage, yeah.
Next.
We should check what pi really is, because we know that pi is a policy, but in this case, I think the policy is going to be a function, so, and it's going to take as input the environment and the state. So I shouldn't call it like this. I should check if pi is callable, then u equal pi mx, else do this. Because pi can be either a function or a vector. If it's a vector, then I just access it through square brackets. If it's a function, I need to call it. I don't know. I don't remember if it is pi is callable or callable pi. Let me check. No, it was the other way. Callable pi. So sorry. This is callable pi. Yeah. This is how you check if a given object is a function or not. Check if pi is a function. Otherwise, assume it's a vector. So now we have run one episode, and we have stored all the information inside this to list. X list contains the list of the states we have visited, and cost list is going to contain the list of the cost we have received at each step of the episode. Now we need to implement, well, not implement, we need to compute the cost to go for every state we have visited. And the comment suggests to do that by moving backward in time, because it's gonna make it a bit easier. Maybe we could also start doing it moving forward in time, because that's actually easier to think about, but it's inefficient in terms of implementation. And then after we have that working, we translate that in the backward way, which is more efficient. Okay, so let's try to do that. For T in range max episode length. So first time we're going to be time 0, and we need to compute the cost from that time until the end of the episode. How do we do it? We can create the variable j, which is the cost to go. We initialize it with 0, and then we need to sum to it all the costs inside the cost list. Okay, so we're gonna have to do another for loop. Can do it for k in range. What should be this range? Yeah, but all of it? Because we are sitting at time t in the episode, and we need to compute the cost to go from that time until the end.
So then it's just from T to max.
Yeah.
Max and episode length.
Exactly. So we go from T to max episode length.
How do we scale for the other for loop?
Yeah, you're probably right. So we should use another name like I. So if we do that, then we are just computing the total cost, but we are not discounting it. So we need to add the discount factor. And the discount factor is going to be gamma to the power of what?
T, I think. I plus T.
Okay, you've tried a bunch of them. Now let's try to reason. So when you're at time t, which could be anything between 0 and the episode length, how much are you discounting the cost you're receiving right now?
No.
Not at all. Okay, so you cannot discount by t, because that would be the same regardless of where you are. Instead, you want how much you discount the cost at a given time depends on where you are right now. So if you're at the beginning and you're looking at the cost you receive in the middle of the episode, then you're discounting it by a lot. But if you're in the middle, then the same cost is not discounted at all because that's the present for you. Okay, so you cannot use t.
The mass length minus t.
No.
But wouldn't it be I then? Because I goes like depending from where we start with t. And
I goes depending on where we start, but I starts from t, which means that it's not going to be 0 except for the very first, except when t is 0.
so is it I minus t?
Yeah, it's I minus t. So it's gamma to the power of I minus t. Because if you think about it, since I starts from t, then the first iteration here, I minus t, is always going to be 0, which is exactly what you want. You want not to discount at all the cost you're receiving right now. And then the second loop, this I is going to be equal to t plus 1. And so when you do I minus t, you're going to get 1. And so you're discounting with gamma the cost of the next time step, and so on and so forth. So in this way, we are computing the discounted cost to go. And now that we have the discounted cost to go, what we can do is to say, well, the current state is simply going to be x list of t. The current cost, well, no, we don't need the current cost. Then we can simply increment the counter for that state, increment the cumulative cost for that state, and update the estimated value for that state. So these 3 lines are exactly the 3 lines that we had in the slide. Increment the counter n, increment the total cost c, update the value c divided by n.
I think I can get why we have the double for loop.
So we run an episode. So in this episode, we visit a bunch of states. Then for every state that we visit, we need to compute the cost to go from that state until the end of the episode. So this for loop here is for revisiting all the states inside the episode. And then for every state inside the episode, we need to compute the cost to go. And the cost to go is a summation from that state until the end of the episode. So for doing that summation, I need a second for loop. Okay. Otherwise, I cannot do this summation if I don't do a second for loop.
So I execute all the episode at once, and then I calculate at the end the cost for each episode.
Yeah, because to compute the cost at time 0, so the cost to go at time 0, I need the instantaneous cost for all time step from 0 until the end. So I cannot compute it before the episode is terminated. Okay. So I need first to run the episode until the end. And then I need to compute the cost to goes for every state that I visited. So you need all these for loops. Well, then we're going to make it more efficient by doing this computation moving backward in time instead of moving forward in time, as the comment suggests. But I think that's to start with, maybe it's better to implement it in this inefficient way moving forward because it's easier to think about. So the algorithm is finished. Now, as usual, we want to just compute the error and to print some stuff to give feedback to the user, which is us. So let's compute the error of the value. So I'm going to compute the average absolute value of the difference between the current estimate of the value and the real ground truth value. So the real was simply passed to this method as one of the inputs. It's here, the real. Actually, now that I think about it, the error should be a list. So instead of doing equal, I'm going to do an append to add that to the list. And then I'm going to do if k percentage and print equal to 0. Then I'm going to print some stuff. Print Monte Carlo, iteration k, and then the error equal the error of -1. And then if plot is equal to true, I'm also gonna plot some stuff. And that's it. So now we can try to run it. So this is the real value function that I would like to estimate. It's one computed with policy evaluation. And then it's gonna start Monte Carlo. Well, at the very first iteration, the value table is just all 0. After 200 iterations, it's already interesting. And we can see that the error we are making has been going down quite a lot. We went from 1.4 at the very beginning to 0.3 after 200 iterations. Then we keep going. We're to 0.17, 0.11, 0.03. And that's it. And this is the plot that we get at the end, which shows the estimation error over the number of episodes. And we can see that we have this monotonic decrease in the estimation error, going from 1.4 at the beginning until, I don't know, 0.03 at the end. Sometimes we hit a plateau, but then there is some improvement which is reasonable because it's a random algorithm. So it's not guaranteed that every new episode we improve. It depends on the states that we visit. If we visit the state for which we already had a good estimate of the value, then there is no improvement. So we only see improvement when we visit new states that we haven't seen before. And that can happen at random times, at random episodes. Another interesting piece of information that maybe we can print is the number of states that we have not visited yet. And I think there is an interesting function in NumPy, which is count zeros, something like that. And we can use that number of states not visited. Not sure it's a correct name.
Actually, it's count non-zero.
Yeah, you're right. Count non-zero. So this is going to be the number of states that we have visited. If I want the number of states not visited, I should do the total number of states minus that. And we can see that the number of states not visited is going down from more than 200, then to 43, then to 14, then to 5 towards the end, and then to 2. So this time we have been luckier. The final error is really small. It's 0.004. And that's connected to how many states we have not visited, which is only 2. So we are almost at 0 error at the end. Well, this case is quite simple because we have a really small dimensional state space and the system is completely deterministic. So we just need to visit each state once to get the value of that state. We don't need to visit it multiple times because there is no noise. If we were introducing some noise, then it would be different. It would take more time to converge. And that's it. That's the implementation of Monte Carlo. So what's left today is implementing temporal difference. Because at the moment, the main script is calling the method temporal difference, but the method is doing nothing. The method is the one below, and you can see it's simply returning a 0 value function, so not really doing a good job. And to implement temporal difference, actually, you will need to start from this code here and modify it because it's not so different. I mean, most of the code is going to remain the same. Actually, temporal difference is going to be easier to implement than Monte Carlo. So I suggest you to just copy paste the code of Monte Carlo inside the temporal difference method. And then you will need to implement temporal difference. We can take a quick look at the slides. So in temporal difference, what you need to implement is basically this equation here for updating the value function. which is much simpler because it doesn't require you to compute the cost to go at the end of the episode. You can just update the value function at each step of each episode. So you need only one for loop, the first one where you run the episode. And at each iteration, you basically collect the cost, you collect the next state, and then you just compute the TD target, which is cost plus discount factor times the value at the next state. This value is your estimate of the value, so it's not going to be correct, but it's fine. That's how it's supposed to work. And then you compute this difference, which is the TD error, and you multiply times the learning rate alpha, and that's the quantity you add to your current estimate of the value of that state. And that's it. That's all the math that you need to have in mind is basically this equation here for implementing temporal difference learning, nothing more. So it should be actually a simplification of the code we have written for Monte Carlo. Do you have any question before we start? Well, before you start. Okay. Then I think you can start. So just take this code. I mean, I'm going to do it as well. And you copy it here. And then, well, if you want, you can follow the comments, but actually, I don't think these comments are super useful. And mainly, you're going to need to remove stuff from the implementation of Monte Carlo and to add maybe a couple of lines for implementing temporal difference. Okay, so maybe you can work on that until 10. So you have 40 minutes. And then from 10 to 10:30, I do the implementation and we play a bit with it. Yeah.
There's something that doesn't work online, and I can't figure it out.
Okay.
It looks the same to me, but
So if you have a problem with Monte Carlo, you're not able to making it work, you can simply look at the solutions which is in the same folder. That should work. Okay. Okay. It's 10 o'clock, so we can start coding together. I see some of you have managed to implement it and it's working. Maybe others have not completed it yet, but we can complete it together. So here is where we were. We don't need these three objects here. We are just going to make a copy of V0, which is the initial guess that we receive in input. So we're going to say that V is equal np dot copy of V0. I think that in this specific case, V0 is simply going to be an array of all zeros, so it's not a very good initial guess. Then for every episode, we want to reset the state. We don't need to keep track of anything in temporal difference, so we can get rid of all of that. And we don't need this stuff here. We don't need this second loop here. So the code just got much, much shorter. Here, and make sure that we are printing the correct name of the algorithm when we print stuff. We cannot check the number of states that we have not visited because we are not using that counter anymore. So far I've just cleaned up the code, removing all the stuff I don't need. And now I need to implement the TD learning update. So the TD learning update is basically this equation here. So V equal V plus alpha times the TD error. So let's do that. So V of X equal V of X plus alpha. Is it called alpha? No, it's called learning rate. Learning rate times TD error, which is cost plus the discount, which is gamma, times V of the next state minus V of X. Then it complains that X next is not defined, and it's right, because here when I'm calling the step function, before what I was doing is replacing the current value of the state with the next value of the state, because anyway I had the X list to keep track of all the states visited. Now I don't have that list anymore, so here I need to give it a different name, like X next. So I have at the same time knowledge of the state at the beginning of the step and the state after the step. And then the only thing I need to do is after I do the update, I also update the state X equal X next. And that should be it. So basically I have 2 lines of code to add and many lines to remove. So it's much simpler to implement than Monte Carlo. Now we need to check if it really works, because I'm never sure that my code works until I run it. Python x3. So this is a real value function computed with policy evaluation. Then I run Monte Carlo. So Monte Carlo was working, no surprise here. And now TD learning. The error is going down. We went from 1.4 to 0.8. Still going down. And now TD learning again, but with a different learning rate, set to 1 instead of 0.5. And this is the final plot. So Monte Carlo is the blue line. So it's the one that is going down the fastest. Then we have the green line, which is temporal difference with a learning rate equal to 1. And then we have the slowest one in terms of convergence is temporal difference with alpha equal to 0.5. So they're all converging, we can see, and we have a monotone convergence. It's never getting worse. But some are converging faster than others. So in this specific case, Monte Carlo is doing better than temporal difference learning in general. And among the different versions of temporal difference learning, we can see that having a higher learning rate leads to faster convergence. But this is a very special case because we are working with a deterministic system. So if you remember, we said that the advantage of temporal difference learning is that while it introduces a bias, it reduces the variance of the target. But here the system is deterministic, so the variance is 0 and you cannot reduce it. it's already 0, which is the minimum variance you can have. So doing temporal difference learning, if you have 0 variance, because the system is deterministic, actually makes no sense, because you're just introducing a bias for no advantage. And so in this case, it's actually reasonable that Monte Carlo behaves better than temporal difference. So now what we could try to do is to go back to the main script and start to play a bit with the noise. So the noise by default is set to 0, but we can set it to 0.1, for instance. And I would remove the plots, however, because that's annoying. Do plots, where is it? Here. So let's see with some noise how the two algorithms behave. So for sure, the error is going to be larger. So already introducing a bit of noise, we can see that the situation is not so great anymore for Monte Carlo. So it's the one doing the best in the beginning, but then after a while, it gets outperformed by temporal difference with alpha equal to 1. And I mean, this is going to change every time you run the script. So you cannot expect to have always the same winner, because now we have stochasticity. Well, the algorithms are stochastic in themselves, because the initial state from which you run the episodes is sampled every time. So even with a deterministic system, the output of the script is going to change every time you execute it. But now we have even more stochasticity, because even the dynamics of the robot is stochastic, because we have added noise in the control inputs, basically. So this time, depending on how many episodes you run the algorithms for, you have a different winner. Also, actually, to be precise, even the ground truth that we are using is no longer a ground truth when we introduce noise, because the algorithm that we use for evaluating the policy, so which is policy evaluation, we are running it before introducing noise. So this noise standard deviation, if you take a look at the code, is actually introduced here, which is after computing the ground truth. Because our code for computing the ground truth doesn't work with the noise. So we are comparing against a ground truth, which is for the deterministic case, even when we are running the stochastic case. So it's no longer a real ground truth, it's just a reference. Okay, so now we have a bit of time left. I suggest we use it for making a better implementation of Monte Carlo, because if you remember, we said that this way of evaluating the cost to goes was inefficient, because we do it moving forward in time, but the comment suggested that we should do it moving backward in time. So anybody has any idea of how we can make this more efficient? Why moving backward in time we can make this computation more efficient?
Because we can avoid forgetting J at every iteration, and we can compute the next J, and by the next I mean the previous.
The previous, yeah.
Backward in time,
by using the cost of the current step plus the discount factor plus times the previous value of J.
Exactly, yeah. So the idea is the following one. Let's say you have J of t plus 1 is going to be L of t plus 1. Well, I don't like this notation. Let's do it like that. Plus gamma times L of t plus 2 plus gamma square times L of t plus 3, etc. So if we do computation moving backwards, and after computing J of t plus 1, we will need to compute J of t. And J of t is L of t plus gamma times L of t plus 1. It's nice to do math in Visual Studio Codes. It's very convenient. Gamma square times L of t plus 2, etc. And we can notice that actually all the terms that were inside jt plus 1, they are also inside jt, because we have lt plus 1, which was here. Well, we have it also here. Lt plus 2, which was here. We have it also here, and so on and so forth until the end of the episode. So we don't need to recompute all the summations of L from t plus 1 until the end, because we already have it computed above, which was at the previous iteration. So what we can do is that we can rewrite J of t as simply L of t plus gamma times J t plus 1. Because we simply need to take these terms here and multiply them times gamma to get basically the tail of jt. So everything that's in jt except the first term was already in jt plus 1, except that we need to multiply times gamma because we need to discount it since it's now in the future. So if we do this computation moving backward in time, we can exploit what we have already computed, which is j of t plus 1, when we compute j of t. And so we don't need two for loops, one inside the other. We just need one for loop. Is that kind of clear?
But that for a loop, we have to start at the max episode length.
Yeah, we need to go backward. So we need to move backward in time. So max episode length is going to be the final value. And sorry, it's going to be the initial value. And the final value should be 0, which means I should stop at before reaching -1. And this step should be -1. So this is how you do a for loop in reverse in Python. You use always the range function, but the range function has some optional input arguments. So if you only specify one value, that's the end. And by default, it assumes that it starts from 0 and it increments by +1. But if you want, you can specify also the initial value and the step. So now the initial value is going to be max episode length. The final value is -1, because then it's going to stop before the final value, which is going to be at 0. And the step is going to be -1. So that's a for loop in reverse. The discounted cost to go, we initialize it outside the for loop now. And now this is going to be simply cost list of t plus gamma times j. So when we start, t is going to be equal to max episode length. Actually, I think it should be -1. That is the last index. So we take the last cost that we have in the list, and we sum to that, well, 0, because at the first iteration, j is equal to 0, which makes sense. When you are at the very last step, there is nothing to add. And then at the next iteration, j is going to be equal to the last cost. So, and then you take the cost at the before last time step, and you sum to that gamma times j, which is the last cost. So it seems to be working. The rest of the code remains the same. So we are just making this more efficient. We can check whether it works. One never knows. The error is going down, so it's a good sign. Yeah, seems to be working because the behavior is kind of the same as before. So Monte Carlo is always the best in the beginning, but then temporal difference is catching up because now we have some noise in the dynamics. So we have some advantage of using temporal difference instead of Monte Carlo. So now, since the system is very small in terms of dimensions, we don't see a big difference in terms of computation time. But if we were running this on a bigger system, then this little change that we just implemented in terms of how you compute the cost to go would have a bigger impact. I mean, probably if you time it with a timer in the code, you're going to see that there is a difference in the execution time. But since everything is so fast here, we don't appreciate it. Okay, I think that's all I wanted to show you today. Do you have any question? Okay, then for the first time in the semester, we are early and we can stop right now. I'll see you on Friday, and on Friday we're gonna finish the lesson on Q-learning and SARSA and start talking about value function approximations.